Okay, so let's get started with so today we'll talk about angle sum identities. So okay, let's see. So if we have two triangles, like let's say this is a 3, 4, 5 right triangle, and let's say the other one is maybe like 5, 12, 13 or something. Then it makes sense that we know this angle is uniquely determined and this angle is uniquely determined. So it makes sense that we should know the sine of the sum of the two angles and the cosine of the sum of the two angles somehow, right? So yeah, can everyone hear me? Okay, so let's just make a general diagram for this. So let's say we have two right triangles on top of each other like this. Okay, so we want the sine of, yeah, sure. Let's say, so let's say I drop an altitude. So I have two triangles, OAB and OAC, and they're right triangles. And then I drop an altitude from C to D, LA, to point D, and then from B to CD. Let's say this is at E. Wait. Yeah. So we want to find sine of, let's write it up here, sine of alpha plus beta equals question mark. So, okay, let's see. So I'm gonna make, I should have said this at the start, but I'm gonna make this length 1. So OC is 1. So I scale the diagram so that the hypotenuse of the biggest triangle is 1. And then, okay, so then what would BC be in terms of like the two angles and 1? So we have a right triangle there, OBC.
Does it have to be both angles?
No, it can just be 1.
Okay. Then BC over, then just BC.
Yeah, so BC over what equals what?
Over 1 equals sine of beta.
Yeah, good, because we have a right triangle OBC, and this angle is beta, so sine of beta is BC over OC. Excuse me. Just BC over 1. So BC is just sine of beta. Okay, so then what about OB? What's OB in terms of beta?
Is it cos beta?
Yeah, it's cosine beta. So cos beta. So I'll put these in. So sine beta. This is cos beta for the whole length. Okay, so now can we get the length of AB? We know the hypotenuse of OAB now. What's AB in terms of alpha and beta? Can we relate the length of AB to another length we know?
CD. Oh wait, no. Never mind. Is it cos beta times sine alpha?
Yeah, good. So we can see sine alpha relates AB to OB. And OB is just cos beta. So this is OB times sine alpha. And then OB was this cos beta. So cos beta sine alpha. Okay, and then what about OA? What's that in terms of alpha and beta?
Cos beta cos alpha.
Yeah, so by the same reasoning, we do the hypotenuse length times cosine of alpha, which relates the other leg to the hypotenuse. So cosine alpha is OA over OB. So therefore, OA is OB times cos alpha. Okay, so we have a lot of lengths. Let's label this as cos beta sine alpha. Okay, so then what would the thing we're looking for sine of alpha plus beta be in the diagram?
CD.
Yeah, so it's CD over OC, and OC is just 1. So that's just CD. So if we can find the length of CD, then we're done. We can find sine of alpha plus beta.
We already know BA, which is DE.
Yeah, good. So we can see that CD is the sum of CE plus DE. It's just the sum of those two segments. Let me zoom out a bit. And then DE is AB, because ABED is a rectangle. Right? This is a rectangle. So yeah, So that means this is cos beta sine of alpha. So we just need to find CE. Okay, so we'll probably have to do something with the right triangle CEB. So if we know the angles in it, well, we'll be mostly done. So what would this angle be in terms of alpha and or beta?
I think it's alpha.
Yeah, why is it alpha?
Wait, alt interior angles.
Yeah, so we can see BE and OA are parallel. So that means this green angle equals this angle, alpha. They're alternate interior angles. Okay, so then let's see, B is a 90-degree angle, so I can write here is 90 minus alpha. At OBC is 90 degrees. And then this is also 90, so I can say this one is alpha. Okay, so then what would be the length of CE now? Can I relate the length of CE to a length we already know? Right, look at triangle CEB.
Cosine alpha equals sine beta. Sine beta over CE.
The other way around, right?
Oh wait, no, sorry. CE over sine beta.
Yeah, so cosine of this angle, alpha, right here, it's equal to CE over CB. So let's just write that down. Cosine of alpha equals CE over CB, which is CE over sine of beta. So therefore, CE is just cosine alpha times sine beta. Okay. So now we know this length is what? Cosine alpha sine beta. Okay. So yeah, so we can plug that into this CE. So this is equal to cosine alpha sine beta, and then plus cosine beta sine alpha. So yeah, so that's our addition formula. So usually it's written like this, sine of alpha plus beta. So this was all equal to sine of alpha plus beta. It's equal to sine alpha cosine beta plus cosine alpha sine beta. This is the sine angle sum addition formula. So just sine addition formula. I guess I'll just write in sine addition formula. Okay. So great. We've proved that if you have two like angles, alpha and beta, and you know the sines and cosines of them, which, like in this example, you know the sine of alpha is 3/4. I mean, cosine alpha is 4/5. Sorry, sine of alpha is 3/5. And you know sine beta and cosine beta, then you can find the sine of the sum of the two angles. Okay, so I guess let's practice with this. Hang on, this diagram probably should look something like that. So it's probably an obtuse angle. Yeah, it should probably look like that. To make it more to scale, maybe I'll color this in black to keep it consistent. Yeah, so the sine one was, so, I recommend memorizing this because we'll have to use this a lot. Okay, so what would sine of this alpha and this beta be? Like this alpha and this beta, where basically sine beta is 12/13 and cos beta is like 5/13 based on this diagram. So yeah, just tell me what to write for the next step.
3/5 times 5/13 plus 4/5 times 12 times 13.
Okay, yeah. So we know all four of these terms. I just wrote them down, so we can just substitute in. So that's 15 plus 48 all over 65. So the sine of the sum would be, what is that, 63/65. Okay, so you can, use it to compute the sum of the sine of the sum of two angles. Okay, so that's great. So let's see if we can do something similar. Just gonna copy this over because it's a decent diagram. So this was a D. So what would a cosine of alpha plus beta be in the diagram? So now we're wondering what is, is there a triangle with alpha plus beta as the angle?
COD.
Yeah. So then what's cosine alpha plus beta? Is it a length in the diagram?
OD.
Yep. So this is OD over OC. So look at this triangle, and then that's just OD over 1. Okay, so it's the hypotenuse 1 times the cosine of alpha plus beta. So we just need to find OD. So similar to before, we'll find OD using some other triangles we know. In particular, we can find DA, and we can find the whole length, AD. So we'll actually be writing OD as OA minus DA. Okay. So let's see if we can first find DA here. So what else is DA equal to in the diagram? Does it equal another length?
EB.
Yeah, so BEDA is a rectangle. So this is EB. And then can I write EB or BE in terms of alpha and beta?
Sine alpha equals BE over sine beta.
Yeah, good. Oh, let's see. So this is, let's write down sine of this alpha equals BE over CB. So that means BE is BC sine of alpha, or sine beta times sine of alpha. Sine beta times sine alpha. Yeah, so it's this length times sine alpha. Okay, and then what about OA? Can you find the length of OA? Is OA part of a triangle with alpha or beta as a acute
This
angle?
is cos alpha times cos beta.
Yeah, so we can look at triangle OAB. And then, so the hypotenuse length is cosine beta. And we multiply it by cosine of alpha. Because cos alpha equals OA divided by OB. Okay. So that's using this little angle here and OAB. Okay, so then we can substitute in. So this angle, OA, we just found that to be cos alpha, cos beta. I wrote it in a different order, but it's all multiplied together, so it doesn't matter. And then DA, which is BE, this dA becomes BE, which is sine alpha sine beta. So yeah, so that's the addition formula for cosine. So cos alpha plus beta is OD, and OD we can find to be OA minus DA, which is this minus this. So this is equal to cosine of alpha plus beta. So again, I recommend memorizing this one. Let me write it, so that this is on the left. Cosine alpha plus beta is cosine of both angles multiplied together. Cos alpha cos beta minus sine alpha sine beta. So notice the plus sign, you have a plus sign here, but a minus sign here for cosine. And the cosine is with the cosine. And the sine is with the sine. So that's a little different than, here you have plus sign and plus sign. But it corresponds correctly, plus sign with plus sign, and you have the sine with cosine and the cosine with the sine. Okay. So, I guess let's draw in that triangle again. What was it again? 3, 4, 5. And 5, 12, 13. It's not a very good right triangle. Okay. So then if this is alpha and this is beta, what would sine of this alpha plus, cosine be using this formula? Well, what should I write down? So I'll just copy what I just wrote. So yeah, so let's see. Cos alpha is 4/5 in the diagram. Beta, cos beta, 5/13 minus sine sine, so 3/5. And what was it? 12/13. So 20 minus 36 equals negative 16 over 65. Okay, so actually this is an obtuse angle. So, okay, so we get that. And earlier, I think we had said the sine of the sum of the angles was 63 over 65. So does this make a Pythagorean triplet? So, we can check this. Maybe the easiest, this, you can change it to a plus sign because we'll square it anyways. So let's see if 16 squared plus 63 squared is this, if it satisfies the Pythagorean identity. Or in other words, if this is true, if the cosine squared plus the sine squared equals 1. So if I move this to the other side, I can use difference of squares. So this equals 16 squared, and this equals 2 times 128 if you add them up. So that's 63 plus 65. And yeah, that equals 16 squared. This is 2 to the 8th equals 2 times 128. Check. Okay, so that's right. Well, at least it satisfies the Pythagorean identity. And we proved the formulas, so it should be right. Let's see, one sec, let me open. Okay, so far, these are the two things we know. We have angle addition formulas. So I'll just say angle addition formulas. So how do you think we might get a tangent addition formula? How can we rewrite tangent of alpha plus beta? So what was our definition for tangent again? Using the unit circle? Or I guess the unit circle defines cosine and sine. So what was tangent in terms of cosine and sine?
Sine over cosine.
Yeah, so that's the definition. Once we define cosine alpha using the unit circle and sine alpha as the y coordinate of the unit circle point, then this is just sine over cosine. So that's the definition of tangent. Okay, so let's just blindly so I guess we can plug in the formulas we just found, right? So if we just rotely so sine alpha cos beta, sine beta cos alpha over cosine alpha cosine beta minus sine alpha sine beta. Okay, so it turns out that the tangent addition formula, it actually, it's in terms of tangents. It looks like this. So how can we get our expression to look more like tangents instead of sines and cosines? Yeah, let me give myself some room. Whoops. So it turns out we'll have to divide the numerator and denominator by something. What might we divide them by? Right, maybe this 1 corresponds to this part. So if I divide both the numerator and the denominator by something, how do I make the cos alpha, cos beta become 1?
You can divide it by cos alpha times cos beta.
Yeah, so I'll just divide the denominator by cos alpha, cos beta, and divide this also by cos alpha, cos beta. And I'll divide this by, okay. So then what does this equal? Let's see. So here we have a sine alpha. I mean, we have a cos beta and a cos beta. Those will cancel out. So then what's sine alpha over cos alpha? So sine alpha over cos alpha, it'll be tan alpha. Whereas here we have cos alpha and cos alpha, and we're left with sine alpha, sine beta over cos beta, which is tangent of beta. So let me, I could write in the intermediate step. And then here we just have 1. And then sine alpha over cosine alpha, that's tangent of alpha. And sine beta over cos beta is tangent beta. So yeah, so this is the tangent addition formula. So if I know the tangents of two angles, I can find the tangent of their sum. So, let's just do it with our other triangle here. So 5, 12, 13, 4, 3. So tan alpha plus beta is, I'll write down the formula again, tan alpha plus tan beta over 1 minus tan alpha tan beta, and then, so tan alpha is 3/4, tan beta is 12/5, and then 1 minus the product, so 1 minus the two things above times together. Oh, whoops, what is that, 12/5? Oh, no, that's right, okay. So that's, let's see, so on top it's 15 plus 48 over, this is 20 minus 36. So that's 63 over negative 16. So that makes sense. Earlier we found that, the, oh, whoops. Where was it? The cosine was negative 16 over 65. And sine was 63 over 65. So if I divide the sine by the cosine, I'll get 63 over negative 16. So that equals sine alpha, which we found earlier, over cosine alpha, which was 63 over negative 16. So that checks out. Okay. So now we have the 3 addition formulas. So what if instead, you know, you have a geometry diagram, which is something like, now let's say you have, well, we could use like a 5, 12, 13 again. But now, let's see. So you have a 3, 4, 5 triangle like this. And you want to find, so this angle is going to be alpha. So AOB is alpha, and this angle is beta. So AOD is beta. And you want to find this angle, alpha minus beta. What's the sine and cosine of that angle? Because maybe, you know, you drop an altitude and you want to find, you know, what are the dimensions of that triangle. So let's say that's C, COD. So these are angles. Angle COD is alpha minus beta. So how are we going to get a subtraction formula if we know an addition formula? So these are the 3 things we know. Let's take the sine one, for instance. How can we get something for sine of alpha minus beta? Is there,
You make the angle at O alpha and then maybe angle B beta and then try to find those.
I didn't catch the end of what you said.
You can try to find the angle at O minus the angle at B.
Well, so the thing is, like, these angles are not nice numbers. Like, they're not a nice number of degrees, and they're not a nice rational multiple of pi in radians. So, you know, like, I guess you could say beta is like arc tan 3/4, and alpha is something like arc tan 12/5. But we can use these formulas directly. Is there something I can replace beta by to make it, well, this expression? So we have to use the addition formulas because that's all we know. And, you know, maybe I could draw a diagram geometry wise and do something similar to the derivation last time, but.
Negative beta.
Yeah, so if I plug in the second angle to be negative a variable, like negative beta, then what does this equal now?
Sine alpha cosine beta minus sine alpha cosine alpha. I mean sine beta cosine alpha.
Yeah, so I'll do it step by step. First, I plug in the negative beta, and then sine of the negative beta cosine alpha. And then you had it right. So what's cosine of negative beta?
Cosine beta.
Yeah, so this is just cosine beta because last time we learned, you know, cosine is an even function. So if you have a beta, you know, these two angles have the same cosines, beta and negative beta. They have the same x coordinate on the unit circle. And then what's sine of negative beta?
Negative sine beta.
Yeah, so this is negative sine beta. So yeah, we can just replace it with, basically it looks the exact same, except instead of a plus sign, there's a minus sign. So yeah, it's pretty easy to remember. If you can remember the addition formulas, you just switch the signs for this subtraction formula. So what if we did the same thing with the cosine? So this is cosine alpha plus negative beta. If I plug it in blindly, I'll get cos minus sine alpha, sine of negative beta. So again, the cosine negative beta is the same as cosine of just regular beta. And we'll have sine alpha negative sine beta, because sine negative beta is negative the sine of beta. So yeah, so this time we'll get the same thing, except the minus sign becomes a plus sign. So cosine alpha minus beta, the minus sign, this will be, you'll have a plus sign. And the cosine is with the cosine, the sine is with the sine. Okay. So then what about tangent? So let me just underline these results. Sine subtraction, cosine subtraction. So tangent, I'll just write it like a minus b. So this is, the tangent addition formula was tan A plus tan B over 1 minus tan A, tangent of, well, B. So B was negative B, since that's what I plugged in for the second variable. So yeah, so what's tangent of negative beta? In terms of tan beta or B? So if I have the sine, tangent is sine over cosine. The sine, the next sine negative beta is negative sine beta. Well, cosine remains the same. If you take the negative angle, the cosine remains the same. So this is sine divided by cosine. So you'll switch the sign. So negative tan beta, 1 minus tan A, negative tan beta. So basically what you get is tan A minus tan B over 1 plus, let me write it down here. So this is tan A minus tan B over, and then two negatives, tan 1 plus tan A tan B. Yeah, so here notice that both signs switched. This became negative, whereas the minus sign became a positive. But otherwise it looks the same. So yeah, so these are all 6 addition and subtraction formulas. So if I recommend just like memorizing the addition formulas, and then the subtraction ones are easy. You can get them easily from the addition one. If you ever forget, just plug in the negative variable and you can figure it out really quickly. But yeah, so these three I would say memorize, because yeah, you'll probably need them in like, well, just to do harder trig and geometry problems, but also maybe in calculus. Okay, so let's take a 5-minute break and we'll resume at 8 a.m. my time. So yeah, after the break, we'll look at a problem, but let's take a break first. Okay, I guess let's get started again. Actually, I think I'm gonna skip this problem because no, well, we can come back to this later. So let's just take a look at number 5 and yeah, see what you get. And I guess you can whisper me your answer. Yeah, so how can we find, oh, okay, let's see. Okay. So if we want to use the cosine addition formula, we'll have to know sine and cosine, right, of both angles. So what's cosine of alpha here?
√5/3.
Mm-hmm. Yeah, so if I draw this diagram, you can see this is √5, so this is √5/3. And similarly, this is √24 or 2√6. So sine of beta, which we're not given explicitly, is 2√6/5. So then if we use the cosine addition formula, it's cosine cosine. I'll just write an abbreviation minus sine sine. So, and then I just put in the two angles, alpha, beta, alpha, beta. And then, so that's, let's see, 5/3. Beta was 1/5. And this was, alpha was 2/3. Beta was 2√6/5. So then we get 5/15 minus 4√6/15. And it's, yeah, so whenever you do the sine addition and cosine addition, you should get like similar denominators. So you can combine it to a single denominator. Okay, so here, I don't know why my worksheet doesn't, yeah, so I think we should, so how can we find this cosine of 75 degrees?
30 plus 45.
Yeah. So then see if you can compute what this equals. And also, I'll make this problem 1 and problem 2, I guess. See if you can find sine of 75 as well, using the sine addition formula. Okay, so this is, let's see, root 2 over 2 cosine 30. That I just plugged it into the cosine addition formula. So cos 30 is root 3 over 2. And then, yeah, this is the same as, this is half. So yeah, so when we do this, this is root 6 over 4 minus root 2 over 4. So root 6 minus root 2 over 4. It's fine. You can show your work in chat if you want. That's fine. It's probably good to do that in general. But you can also just write it on paper. That's fine too. Okay. So sine 75. We break it down the same way. And then I just plug in to the sine addition formula. So sine first angle, cosine second angle, plus cosine first angle, sine of second angle. And then let's see, so root 2 over 2, 3 over 2 plus root 2 over 2, 1/2. So it looks pretty similar. This is root 6 plus root 2 all over 4. Okay. So just as a little bit more exercise, can you use the subtraction formulas to find cosine 15? And so how should we rewrite 15?
45 minus 30.
Yeah, so just to practice using the subtraction formulas, yeah, do this and this. And see what you get. Okay, so let's just practice using the subtraction formulas. So here we'll have a plus sign, cos plus sine. And here we'll have a minus signs. Well, okay, let's first finish this. Root 2 over 2. Cos 30 was root 3 over 2. This is root 2, 1/2. So root 6 plus root 2 over 4. And then this one, Well, so notice this is the same as sine of 75. Earlier we found sine 75 to be the same thing. And that makes sense because, you know, if this is 75, then this is 15. So cosine 15 is a over c, and sine of 75 is also a over c. Okay, that means, you know, this one we could just say is cosine 75 and look at our answer from above. Root 6 minus root 2 over 4, but, you know, if we want to just check it, so sine cosine minus sine of the second angle, cosine of the first. So that's, and yeah, that's the same thing. We get root 6 minus root 2 all over 4. So cos 75 is a over c, sine 15 is also a over c. Okay, so one more practice. Find tangent of 75 using the tangent addition formula, and find tangent of 15 using the tangent subtraction formula. Okay, let's see. So this is tan A. Over 1 minus tan A tan B. Okay, so this was tan 45 is 1. Tangent of 30 is root 3 over 3. And this is 1 minus the product. Okay, so this is over this. Then we get this over this. And then we can just rationalize. So multiply by root 3 plus and 3 plus root 3. So this is 9 minus 3 over, if we square it, it's 9 plus 2 times root 3 times 3 plus 3. And then we'll get 12 plus 6 root 3 over 6. So that's 2 plus root 3. Okay. And, how else could we have gotten this based off of our previous work from above? How can we, what's another way of finding tan 75? If we already found sines and cosines. I don't know if you said something, Anya. Let's see. So it could be sine of 75 over cosine 75. Oh, yeah, I don't know if it was lagging or something. So let's see, sine of 75. So here's the diagram for it. Like, I think earlier we found that sine 75 is root 6 plus root 2 over 4, and cosine 75 is root 6 minus root 2 over 4. So, just to check, if I square this, this is 6 plus 2 minus 2 root 12. If I square this, this is 6 plus 2 plus 2 root 12. So these two add up to 16, which is 4 squared. So that's right. So, if we really wanted to, we could have just done, like if we had sine 75 memorized, it's root 6 plus root 2 over 4 over root 6 minus root 2 over 4. So sine 75 over cos 75 is equal to that. And that's tan 75. So, this is the same thing. The 4's cancel. And then, I can cancel out a root 2. So this is this over this. And then it's the same thing as this. I could have canceled out a root 3 from above. So then you can just rationalize again. And you'll get the same thing. This is 4 plus 2 root 3 over 2, which is 2 plus root 3. Yeah, you can get it in multiple ways. Okay. So let's try. Okay, so here's something. How can we get tan of 105 using what we found so far? So there's two ways. So here's 105. How can we get, yeah, let's say tan of 105. Is it related to anything we found earlier?
+90 15.
Yeah, so we could do that.
Or 70, wait, no. 75 + 30.
Okay. So both of these are valid valid suggestions. But you know, if we don't, what if we wanted to avoid like multiples of 15 that aren't 30 or 60 multiples of? What if we only want to use 30, 45, and 60, or 90 plus or minus that? So I don't know if this is easy or this is easy. I mean, I guess we already know tan 75. But you know, if we didn't know tan 75, it could be tangent of 60 plus 45, right? And these are easy values we know. So, you know, this would be tan 60. But is there another way we could figure it out? How's tan 105 related to tan 75? Are they equal? So here's 75. Or are they, how are they related? So notice that both of these are 15 degrees from 90, right? So if I drop the altitude, you know, how are the y coordinates related and how are their x coordinates related for their terminal points? Do they have the same y coordinate?
Yes.
Yeah, and they have opposite x coordinates, right?
Yep.
So that means, you know, if this is sine 105 over cos 105, the signs are the same, right? They have the same y coordinates. And the cosines are opposites of each other. So they're just negatives of each other. And earlier we found that tan 75 was 2 plus √3. So that means tan 105 is just negative that. And you know, it makes sense, you know, like you should do some estimation and see, you know, oh, you know, this looks like 75 degrees. You know, this is like 2 plus √3 and versus 1, right? You know, that seems reasonable. This is about 3.7. You know, that seems reasonable if I draw an accurate 75, 15, 90 degree triangle. Seems reasonable. You know, if you get like, for instance, if you somehow got tan 75 equals 2 minus √3, you would know something's wrong because 2 minus √3 is like, what, 0.28 something? I don't know, 0.27 something. It's 2 minus 1.73 something. 1.732. So, that doesn't look right. If this was 1 and this is 2 minus 1.7, then, it's clearly, something's clearly not to scale in our diagram if this is 75. So, you should, do some estimations and check that your answer is roughly in this right ballpark of a correct ratio or measurement. Okay, so what if I wanted to find let's say tan, well, it doesn't have to be tangent, but let's do tangent 195. How's that related to something else? Oh, did we find tan 15? We never finished finding tan 15. Well, so how is this related to tangent 15? Are they equal? Or are they negatives of each other?
I think they're equal.
Let's see, so 15 is there. This is 180 plus 15, so 195 is there. So they're diametrically opposite. Yeah, so why are they equal? So let's see. The sine of 15 will be negative sine. Yeah. So basically, this has negative sine and negative cosine. This has positive sine and positive cosine for that angle. So when you divide them out, the negatives will cancel. So this equals this. And cosine 15 equals negative cosine 195. So yeah, so these two are equal. And it turns out, let's just compute tan 15. So I guess I'll do this one. So if we use the tan subtraction formula, it's tangent of the first minus tangent of the second over 1 plus the tangent A tangent B. So 1 minus tangent 30 is yeah, it's like this over 1 plus this. And this looks very similar to something we had earlier. So this is root 3 minus 1 over 1 plus root 3. If I change this to 1 over root 3, it looks like that. And then and then I can multiply by root 3 minus 1 over root 3 minus 1. So then it becomes 3 minus 1 is the bottom by difference of squares, and this is, you square it, so 3 plus 1 minus 2 root 3. And then this is 4 minus 2 root 3 over 2, or 2 minus root 3. So yeah, it's actually looks similar to tangent of, it looks similar to tangent 75. So it's, you could have this memorized if you really wanted to. So the basic diagram is this is 4, this is 2 plus, no. This is like root 6 plus root 2 over 4. I mean root 6 minus root 2. And then the ratio of this divided by this is equal to 2 plus root 3. So this is 75, this is 15. You don't have to memorize it, but it's useful for math competitions to have it memorized sometimes. So, or you could scale it down by 4. If this is 1, this is root 6 minus root 2 over 4. Root 6 plus root 2 over 4. And then the ratio of the longer side to the shorter side turns out to be 2 plus root 3. And the other way around is 2 minus root 3. So, if you want to, you can memorize this. I have it memorized because it's useful for math competitions. Okay. So, So let's revisit this problem again. So why do you think we need to know that alpha and beta are both in the first quadrant? Why is that a necessary clause? Could the answer be different if it didn't say that? I think the answer was something like over 15 or something.
If it wasn't in the first quadrant, you wouldn't be able to use the Pythagorean theorem. So it'd probably be different.
Okay, yeah. So how many angles have sine of alpha being 2/3?
2.
Yeah, one of them is in the first quadrant. Where's the other one?
Second.
Yeah. So then what would be the cosine of alpha if it's in the second quadrant? Whoops. This is a horizontal line. So this could be another alpha. I'll call it alpha 2 for the whole big angle here. So how is the cosines of alpha and alpha 2 related here? So this is alpha 2. So that means this is alpha, right? So the cosine of this alpha and this alpha 2, they should be negatives of each other because we're just reflected over the y-axis. So yeah, so so here we could have cosine of alpha be plus or minus root 5 over 3. Because the normal way you find, recall the Pythagorean identity. It says cos squared plus sine squared is 1 for the same angle alpha. So if sine alpha is 2/3, then cos alpha could be a positive or negative number. So if we're not told that alpha is in the first quadrant, it could be in the second quadrant, in which case cosine alpha is negative root 5 over 3. So there's two possibilities. And it's the same thing for cosine beta. you could be in the first quadrant or the fourth quadrant. Because you could have like 1/5, 1, 1, and then this could be 2√6/5 or like negative 2√6/5. So yeah, so there's two possibilities for the sign of beta if we're not told that beta is in the first quadrant. Okay, so let us what if we wanted to find tangent, no, let's say sine of 2 alpha. So, you know, if I know, let's say sine alpha is 3/5, and I just stack two of these triangles on top of each other, you know, I should be able to figure out what is, you know, let's just draw it like this. So this is 3/5, this is 3/5. I should be able to figure out what is, you know, the sine of 2 alpha, like the length from D to E here, the vertical length. So how can we find an expression for sine of 2 alpha? How can I rewrite the 2 alpha?
Alpha plus alpha.
Mm-hmm. So then what do I get if I use the addition formula?
Sine alpha times cosine alpha plus cosine alpha. Just 2 sine alpha cosine alpha.
Yeah, so I'll get, you know, these are the same thing. I usually write the sign first, but it doesn't really matter. So yeah, so we'll just get two of these. So this is called the sine double angle formula. You don't have to memorize it because you can just plug in alpha plus alpha into the addition formula. And if you have the addition formula memorized, you can quickly figure this one out in like a few seconds. What about cosine 2 alpha? What if we tried the same thing?
Cos squared minus cos alpha squared minus sine alpha squared.
Yeah, so we have cosine of the first, cosine of the second, minus sine of the first, sine of the second. So this is cos squared alpha minus sine squared alpha. So this is the cosine double angle formula. And again, if you know the addition formulas really well, you can not memorize this and you can figure it out in about 10 to 20 seconds if you need to. If you want to memorize it, that's great too. That's probably useful. But the more important thing is, you know, can you figure it out, rederive it, and, you know, if you know the addition formulas for sine and cosine, you can figure both of these out. Okay. What about tangent double angle? I'll just write it out A plus A. What's that going to be? Let's see, we'll have tangent A plus tangent B over 1 minus tangent A tangent B. Oh, but B is the same as A here. So here we get tangent of double an angle is just 2 tan A over 1 minus tan squared A. So that's the tangent double angle formula. And again, it comes from the addition formula. So it's good to have it memorized, but it's more important to have just the addition formula memorized. The addition formulas lets you derive the subtraction formulas and the double angle formulas. Okay, so what if I wanted to find, like, what if I wanted this in terms of only cosine? What could I do? So I don't want any sine alphas in my expression.
Is it 1 minus cosine alpha squared?
Yeah, right. So the Pythagorean identity, we can relate cosine alpha squared with sine alpha squared. They always add up to 1. So this is 1 minus cos squared alpha. And then if we expand it out, we'll have 2 cosine squared alphas minus 1. So this is an alternative way to write the cosine double angle formula in terms of just cosine. And then if we know only the sine, we could rewrite this as cosine squared is 1 minus sine squared alpha. So we could also rewrite it like 1 minus 2 sine squared alpha. So yeah, there's 3 forms of cosine double angle formula. And I wouldn't really recommend trying to memorize them all 3 at the very start. I have a bad memory, so it's more important to be able to rederive them. If you know this, and you know this relationship, you can easily find the other 2 forms. So I wouldn't worry too much about memorizing all 3 at the start. You can rederive all 3 of them. Okay. So let's say I give you 2 problems. I don't know which number this is, but so let's say sine alpha is 3/5. So part A is alpha is in quadrant 1. Part B is alpha is in quadrant 2. So in both cases, can you find sine of 2 alpha? Okay. So what would be the cosine of the first alpha? Let's see, this is 3.
4/5.
Yeah, and what about the second alpha?
Minus 4/5.
Yeah. So the sine double angle formula was 2 sine alpha cosine alpha. So that's 2 times sine is 3/5. That's given. And the cosine here is positive if it's in the first quadrant. So this would be 4/5. I need to use the thicker marker or else I can't see my cursor. So 24/25. Whereas here, you'll get 2 alpha, sine alpha cos alpha is 2 3/5 negative 4/5 all multiplied together. So that will be negative 24/25. So let's just make sure that this makes sense. If I have this angle where the sine of it is 3/5, if I double this angle, it looks like it might be in the first quadrant, right? So this is also 3/5. Okay, this is not a good diagram, but so if I double the angle, so alpha and alpha, like sine of 45 is let's compare alpha to 45 degrees. Sine of 45 is root 2/2. That's about 1.41/2, which is about 0.7. It's bigger than 0.7. Whereas sine of alpha is 0.6. It's 3/5, which is 0.6. So that means 45 is bigger than 3/5. So, if I draw in this line, the 45-degree mark is like, there's maybe 3/5. The 45-degree mark is right there. And here's alpha. So if I double alpha, it'll be less than 90 degrees. Because sine is an increasing function from 0 to 90 degrees. If sine alpha is less than, if alpha is less than beta, or 45 in this case, then sine of alpha is less than sine of beta, where these are between, 0 and 90. It's because sine is an increasing function from 0 to 90 degrees. It increases from 0 to pi/2. Let's make sure the other one makes sense too. So, I like to, just kind of visually see that these makes a little bit of sense. So here's the other alpha. The sine is 3/5. The cosine is negative 4/5 is the x-coordinate of that point. Now let's see. By the same reasoning, this is bigger than 135 degrees. So that's the 135-degree mark. If I double it, it'll be bigger than 270 degrees. So if I double this angle alpha, it'll be somewhere right here. 2 alpha. So 2 alpha will represent this blue angle. And yeah, so this, So this will have negative, we found that sine of 24/25, sine of 2 alpha is negative 24/25. And it makes sense. Both this point and this point, will have negative signs. So what about cosine of 2 alpha if alpha is in the second quadrant? What would that be? Well, I guess, let's just do it together. So cosine alpha was 3/5. If it's in the second quadrant, sine alpha was 3/5. Cosine in the second quadrant is -4/5. And these satisfy this squared plus this squared is 1. So if I use the cosine double angle formula, let's see, cosine 2 alpha is cosine squared alpha minus sine squared alpha. So that's -4/5 squared minus 3/5 squared. So that's going to be, well, it's going to be 16 minus 9/25. So this is a positive number. And it makes sense because, we saw here this angle is right above 135 degrees. So this is right above 270 degrees. So it makes sense that this is positive. This is 7, this is 24, this is, if I scale it to 1, this is 24, and this is 7/25, 24/25. So yeah. So even though this is in the second quadrant, when I double it, it doesn't go to the third quadrant, it goes to the fourth quadrant. Because if it was less than 135 degrees, like right here, then double it would be less than 270. It might be right there. And then the cosine would be negative. So I just like to check the quadrant makes sense geometrically, like with a rough picture and kind of estimating some lengths. Okay, so let's see. We'll stop here for today. There are some exercises in the handout that I'll ask you to do. And yeah, we'll stop here for today. Are there any questions? Okay, there's about 27 exercises related to the addition formulas and subtraction formulas and I guess double angle identities, but I think we've done some of them, and the handout approaches the proofs in a different way, so you don't have to do all the proofs at the start of like questions 1 through 8 or 9 or so. Okay, so yeah, we'll focus pretty much all exclusively on trig and hold off on the geometry problems for the next few weeks. But do send me, geometry problems that you want to go over, and we'll go over them in future weeks. I made a spreadsheet of like the problems you've sent me so far. Okay, yeah. So thanks for coming. See you guys next week.
Bye.
Bye.